All right, let's move on with the electronic spectra. In the last class, we have looked at metal ions in an octahedral ligand field and how the terms split in an octahedral ligand field. And we have derived correlation diagrams that basically tell you how the energy of the terms change as a function of the strength of this ligand field. And a result of that was that we would, according to that, expect a lot of possible electron transitions. And that would lead to very complicated electronic spectra. However, nature makes it a little bit easier for us because of what is called the selection rules. And I've told you that there are two selection rules, the so-called spin selection rule and the Laporte selection rule. So the spin selection rule says that only transitions with delta S is equal to 0 is allowed. Okay, so the spin multiplicity cannot change during a transition. So for instance, you can excite from a singlet state to another singlet state, but not from a singlet state to a triplet state, for example. And there's also the Laporte rule that says that only transitions with change of parity are allowed. So for instance, from G to U or from U to G. However, I also told you that the Laporte rule doesn't hold strictly. It only diminishes the intensity of the transition because it diminishes the likelihood for this transition to happen, but it does not actually forbid it. Okay, but the selection rule holds strictly, and the transition is really practically forbidden. Okay, so now based on that, we can now predict our electron transitions for an octahedral complex. And these electron transitions can be, again, predicted on the basis of selection rules and the correlation diagram. Now, you see here a particular kind of correlation diagram, which is called a Tanabe-Sugano diagram. So this is similar to the correlation diagram discussed in the last class. The only difference is that we have the ground state plotted as a horizontal line, and the energies of all the other states or the other terms is plotted relative to the energy of the ground state. This is useful because in practice, we want to know, well, energy differences relative to the ground state when we excite an electron from the ground state into an excited state. Okay, so now you see that the ligand field strength is again plotted to the right, and the energy of the terms is plotted in the y direction. You see when you look at the units that the energy is plotted in somewhat strange parameters B. So B is a so-called Raka parameter, which is a quantum mechanically derived term that is being used to calculate the energy of the terms. So I do not want to go into more depth here, but just state that this so-called Raka parameter B is nothing else but an energy unit, and it's a convenient energy unit to use because it puts out numbers that are neither too small nor are they too large, so they can be easily read. Okay, so now here to the right we have B values of 1, 2, 3, and so forth. And here in this direction, we have 10, 20, 30, 40, 50, 60, and so forth. So these are just convenient numbers to use. Okay, so you see here, and I maybe remove this so that you can see the title completely. The Tanabe-Sugano diagram for the 2-octahedral complex. And you see that the ground term for the 2-octahedral complex is a triplet term. It's the T1 triplet term. You see here also that the U and G symbols are being removed. These terms that you see here would actually all be G terms, but because we do not consider the Laporte rule, it's just not written out here. Okay, it's just a simplification because we don't need that information. Okay, so then you see here all the terms with higher energy, and what you can see is that some of the lines are straight and some of the lines are being bent, and that has actually a reason. So you see that whenever you have bent lines, then there are two or more terms of the same type. So whenever you have two or more terms of the same type, then that leads to the bending of these lines. And that is because these terms have the same symmetry. Okay, and when terms have the same symmetry, then they can interact with each other. Okay, similar to orbitals. You have learned that when two orbitals have the same symmetry type and fairly similar energy, then they can interact with each other. And the same is true for terms. So the closer they are in energy, the more strongly they interact with each other. And this is actually illustrated here. So let's say here we have the field strength and we have the energy of the terms, and we consider two terms of the same symmetry type. Okay, so without considering the interactions, the energy of these terms would follow straight lines. Okay, it's a function of the field strength. But now, because these terms have the same symmetry, they can interact, and they interact the more strongly, the more similar the energy of the terms are. When you see that here at this point, where the two lines cross, the energy is exactly identical. Okay, so at this point, the two terms interact the strongest with each other. Okay, so overall, that leads to the fact that the energy of these terms follow curves that bend away from each other. Okay, so with the interactions, the energy of the first term here would be this, and the energy of the second term would be that. Okay, you either get concave or convex curves, and you see this also here in this real correlation diagram for specific cases. So, for instance, here, these two lines, they bend away from each other, and you see that they both belong to the symmetry type A1 and 1. So this is a 1 and 1, and this is another 1 and 1. All right, and the bending of these lines can be explained because of the same symmetry type. All right, so now with the help of this diagram, you can now predict the number of electron transitions that we would expect from the ground state. Okay, so our ground state is a triplet state. Okay, so now because of the spin selection rule, we can now only have transitions into other triplet states. So we have to count the number of additional triplet states that exist, and that determines the number of the transitions. Okay, so we have here another triplet state. So the excitation from this triplet state to that triplet state would be possible. So for instance, at a ligand field strength of 2B, okay, the transition would occur if light with an energy equivalent to the length of this arrow here would be used, okay, which would be about 20B. And of course, that could all be interconverted into joules or the wavelength in nanometers and so forth. Okay, so what other triplet states do we have? Well, here we have another triplet state, this one here, that allows for another transition. And here we have another triplet state. And is there one more? No, that's basically all. Whereby I see there's one inaccuracy. So this here is actually the triplet state. In that line here seems to be a singlet state. So this arrow here should actually slightly be shorter. Can you see this? The numbers are a little bit small, but this here is actually 3, and that here is actually a 1. Okay, the excitation goes actually into this state here. All right, so now according to the same principles, we can understand the Tanabe-Sugano diagrams of other octahedral complexes having different electron configurations. So for instance, we can go from D2 to D3. And the Tanabe-Sugano diagram of a D3 octahedral complex would look like this. Okay, so now you see that in this case, you have a 4A2 term as the ground state, and so you can predict the number of transitions by looking at how many other quartet states there are. So there is one here, and there is one over there, and there's the third one here. Okay, and that's it. So we would expect 3 possible electron transitions, and the wavelength associated with these transitions would depend on the delta. All right, so now let us briefly understand why this ground state here is actually a quartet state. We can understand that actually from the classical orbital diagram picture. So we have in an octahedral ligand field our T2G and our EG orbitals. And now we have a quartet state as the ground state because we have 3 unpaired electrons. Okay, so therefore our capital S is 3 times a half. Okay, this is 3 half, and then 2s plus 1 is equal to 4. Okay, note though that this particular electron configuration represents only one microstate. Yeah, consider that this quarter term not necessarily only contains one microstate, but there is also another number of microstates possible that have equal energy. Okay, so when we actually draw something like this, okay, then we actually draw the microstate, which gives you the capital L and the capital S values. You can say that this microstate is kind of the representative microstate for the term. But note that this is not the only microstate that belongs to the term. Okay, so now let's go from the D3 to the D4 electron configuration. And you see that our Tanabe-Sugano diagram now looks a little bit more complicated. Okay, you have here this vertical line at a particular P value. And you can see that at this vertical line, the ground state changes. So at P values left to this vertical line, our ground state is a 5e term, and at P values right to that, our ground state is a triplet term. So that is now because with a d4 octahedral complex, you can have high spin and low spin complexes. Okay, so below that value here, our ligand field is, well, weaker than the spin pairing energy, so we're getting a high spin complex. And at B values larger than this, the spin pairing energy is being overcome and we're getting a low spin complex. And of course, the high spin and the low spin complexes must be associated with different ground terms. So we can understand relatively easily why at these relatively low B values we have a quintet term, while at high B values we have a triplet term. Okay, so now we can understand this again fairly easily from our classical orbital box diagram for the octahedral case. So a high spin complex would have 1, 2, 3, 4 unpaired electrons. Okay, so what would be the spin multiplicity for this case? Well, 4 times a half is 2. Okay, and well, 2 is plus 1, meaning 2 times 2 plus 1 is equal to 5. Okay, so this explains why the ground term here is a quintet term. Again, keep in mind that this particular electron, well, configuration here is only one microstate, and there are other microstates possible that have the same energy, but we are drawing this one because it's the one that gives us the capital L and the capital S value. So we can say, well, it's kind of a representative microstate for that particular term. Okay, so now what about the low spin case? Well, when you have a low spin case, then we pair the electrons to the fullest degree possible. And that means that we have only 2 unpaired electrons left. So now, because of that, our S value is 2 times a half, which is equal to 1. And then our 2s plus 1 value is, well, 2 times 1 plus 1 is equal to 3. So our term is a triplet term. Okay. So now again, we can predict electron transitions for both the high spin and the low spin case using our Tanabe-Sugano diagram, but the number of electron transitions will of course be different because we have different ground terms with a different spin multiplicity. So for the high spin complex, we have to look for other terms that are quintet terms. So are there any? Well, there's one here, but that seems to be the only one. So only one transition is possible. Okay. So now for the low spin case, we have a triplet ground term. So we can excite into this 3e triplet ground term. And there's here another one. There's 3a1 and there's a 3a2, which gives you additional possibilities for excitation. So we would overall expect here 3 transitions and 3 bands in our absorption spectrum. All right, oh no, there's even a fourth one. Yeah. There's this E, and there's this 3T2, then there's this 3A1, and there is this 3A2. Yeah, it's all 4. All right. Now let's go from D4 to D5. So now for D5, there's also high spin and low spin possible. So for our high spin complex, we have a 6-state state as the ground state. And for a low spin complex, we have a doublet term as our ground state. Again, we can understand this pretty easily. So our high spin complex would be determined by this microstate here. Okay, so in this microstate, we have all spins up, so 5 electrons are spin up. Our S value would then be 5 times a half, which is 5 halves. And 2s plus 1 would then be 2 times 5 halves plus 1 is equal to 6. All right, that explains this 6th state here. And for a low spin complex, where we have only one unpaired electron left, so 1 times a half is a half, and 2 times a half plus 1 is equal to 2. That explains why we have a doublet state here. So we can again predict pretty easily the electron transitions that are possible. So now we see that for the high spin case, there is no electron transition possible because we have no other 6-state term. Okay, and that means that a D5 high spin ion should be completely colorless. Okay, an example for that is manganese 2 plus. I don't know, ever seen a manganese 2 plus solution, for instance, a solution of manganese chloride, MnCl2. It is pretty much colorless. However, it's a very slightly pinkish touch. Okay, and that is because also the spin selection rule does not hold entirely strictly. So very small probability also these electron transitions happen. Okay, but they're extremely weak. Okay, now when we have a low spin D5 complex, the situation is differently. We have here doublet state, and we have more doublet states. So there is one here. And in addition to that, there is one here. And there is one more here. And that is all doublet states as far as I can see. Yeah. So overall we have 3 transitions. All right. Now what about a D6 octahedral complex? Also here there are high and low spin complexes possible. For the high spin complex, we have a quintet state as the ground state. And for the low spin complex, we have a singlet state as the ground state. Again, that can be explained pretty easily. So for the high spin case, we have 4 unpaired electrons. So S is defined by 4 times a half, which is 2. And then 2s plus 1 is 2 times 2 plus 1, which is equal to 5. So this explains this 5 here. So now for the low spin complex, you see that all the electrons are being paired, no unpaired electron. So S is equal to 0 times a half, which is equal to 0, and then 2s plus 1 is 0 plus 1, which is equal to 1, and that explains the singlet state here. So now which electron transitions are possible? So for the high spin case, do we have other quintet states? And the answer is yes, we have. This is this one here. This one is a quintet state, is shown here. But that's the only quintet state that we have. Therefore, only one electron transition is being allowed. Yeah, that's correct. And for the low spin case, we have to look for other singlet terms. So here, this 1T1 is 1. And then we have another one here, which is a 1T2. And there's one more here, which is a 1A2. And there's even a fourth one here, which is also 1. All right. So now, oh, there's even one more. Oh yeah, this is here one here. One. Now we have more like this. All right. So now for the 7 octahedral complex, we again have high and low spins, always the same game. The high spin complex is a quartet term, and the low spin complex is a doublet ground term. So for the high spin complex, we have 3 unpaired electrons. So S is equal to 3 times a half, which is equal to 3 halves. And then 2s plus 1 is 3 halves times 2 plus 1, which gives 4. That explains this 4 here. So for the low spin complex, we have 1 electron, which is unpaired. So therefore S is equal to 1 times a half, which is equal to a half. And then 2s plus 1 is 2 times a half, which is 1 plus 1, that gives 2. So that explains why this term is a doublet state. So again, what are the electron transitions? So here we have a quartet state, so we have to look for other quartet states. So there is one here. This is this one. Then there's another one, which is this one here. And the third one, which is this one. So it should be over all 3. Okay. So for the low spin complex, we have to look for other doublet states. So we have this one here, then we have this one, and there's this doublet state here as well. So 3 transitions. All right. Oh, there's even one more. Here you have another 2A2. So it's even 4. Okay, so now for the D8 electron configuration, we have again a simpler diagram. That is because for the D8 electron configuration, we cannot have high and low spin complexes anymore. All complexes can only have basically the high spin electron configuration. Therefore, our ground term is not a function of B. It's this triplet term here for all field strength. So now we can again explain why this is a triplet term. So for the D8 electron configuration, yeah, we have 8 electrons. So S is equal to 2 times a half, because we have here these 2 unpaired electrons, and that's 1. And then 2s plus 1 is equal to 3. That explains why it's a triplet term. So how many other triplet terms do we see? There's this one here. There's this one here. This is a singlet. This is a singlet. This is another triplet. And that should be all. So that would be 3 electron transitions possible. And for the D9 electron configuration, we would have the same as the D1 electron configuration. But we only have one term to consider in this case. Okay, so now we are still not quite finished with the electronic spectra, because we have not considered charge transfer, the so-called charge transfer transitions. So thus far we have only considered so-called DD transitions. So the transition of d electrons, which are in a term coming from d orbitals into another term coming from the d orbitals. So we are only considering transitions from d into d. Okay, but this is not the only possibility how electron transitions can occur. In addition to that, you can also have so-called charge transfer transitions. So here are some simple considerations why these charge transfer transitions must happen. So for instance, when we look at a zinc 2+ ion, then that is a D10 ion, and because of that, there are no D to D transitions being allowed. So considering DD transitions only, our ion should be colorless. So zinc 2+ ions are indeed colorless. But that is not always so. So for instance, in this complex here, in which we have a copper 1 ion complexated by 4 acetonitrile ligands, well, in this case, it's also colorless. So also a copper 1 D10 ion should be colorless, and it is. But if you just change the ligand from acetonitrile to phenanthine, then even though we again have a copper 1, which is a D10 ion, our complex is colorful, it's a dark orange color. So here these examples are similar. So in titanium tetrafluoride, we have titanium in the oxidations +4 that makes it a D0 ion. So we have no D electrons, therefore shouldn't have any DD transitions, and we should have a colorless compound. That's indeed the case. For the titanium tetrachloride, we also have a D0 ion, which is also colorless, as we would expect it. But if you go from the chlorine to the bromine, then our compound is no longer colorless. It's actually orange. And if we go from the bromine to the titanium, then we observe a dark brown color. And these colors cannot be explained by DD transitions because there are just no electrons. So some of these compounds are even extremely colorful. So for instance, the permanganate ion is extremely purple. You probably know this, you have seen this in the lab. But well, when you look at the manganese here, then you realize the manganese, the oxidation state +7. So manganese is a group 7 element. So if you remove 7 electrons, you have no d electrons left. So you also have a D0 ion. But despite that, it's extremely purple, extremely colorful. And the same also for a dichromate, which is bright orange, very intensely so. But if you analyze the chromium, then you realize the chromium is in the oxidation state +6. That makes it also a D0 ion. So it should be colorless, but it's extremely bright orange. So now these colors, these electron transitions, can be explained through so-called charge transfer transitions. So what do we mean by that? So there can be two types of charge transfer transitions. So-called metal to ligand to metal charge transfer transitions. So ligand to metal charge transfer transitions happen when you excite electrons from pi molecular orbitals and possibly even sigma molecular orbitals, which are bonding into the metal d orbitals, the T2G and the EG. So why is this called ligand to metal? Because the bonding pi MOs are located mostly at the ligands, or the bonding sigma MOs are mostly at the ligands, while the T2G and the EGMOs are located mostly at the metal. So overall, you move electron density from the ligand to the metal, hence we call it a ligand to metal charge transfer transition. So now, of course, these transitions are only in the visible region if the energy difference between these orbitals here, the pi MOs and possibly all the sigma MOs and the metal MOs is sufficiently small. Okay. On the other hand, we can have so-called metal to ligand charge transfer transitions. So in this case, we excite metal d electrons from either the T2G or the EG orbitals into pi star molecular orbital. So this is called a metal to ligand charge transfer because, well, the metal MOs are located mostly at the metal, but the pi star MOs are located mostly at the ligand. So overall, we move electron density from the metal to the ligand. Again, these transitions can only occur in the visible region if the energy difference between the pi star and the metal orbitals is small enough. Okay. So now we can think about under which conditions these energy differences are small enough so that the electron transitions can occur in the visible region. Okay. Yeah, another thing to consider is, I forgot that these charge transfer transitions are usually both spin and Laporte allowed. Yeah. And for that reason, they can be very intense. And that explains why, for instance, the permanganate ion is so intensely purple and the dichromate ion is so intensely yellow. Okay. So now how can you identify the charge transfer transition? These are often solvatochromic. And that means that the exact color of the ions depends on the solvent. Okay, and that is due to the fact that also the solvent can interact with the ions, slightly changing the energy of the molecular orbitals of the ion, and that results then in a color change of the ion in the respective solvent. So that doesn't affect the DD electron transitions much, because the DD electron transitions happen close to the metal. Okay, because the d electrons are located close to the metal. So solvent has not much of an effect. But when charge transfer from the ligand to the metal or from the metal to the ligand is involved, then the orbitals, the orbital energies of the ligands are a lot more important, and these energies are a lot more influenced by the solvent because the solvent is in direct contact with the ligand. Okay, the solvent surrounds the ligand. All right, but now to the question that I wanted to answer originally. What properties do the metals and the ligands have to have for that ligand to metal charge transfer transition and metal to ligand charge transfer transition occurs. So now let's first look at the ligand to metal case. So the properties of the metal ions would need to be that the valence orbitals should have a low energy, okay, and that is plausible because the lower the energy of these orbitals, okay, the closer they come to the pi MOs and the sigma MOs in energy. Okay, so that makes these energy differences smaller and more likely to occur in the visible. All right, so we have low energies when our metal ion has a high positive charge. So why is that? Because a high positive charge or high oxidation state at the metal pulls the metal d orbitals closer to the metal. So they experience a high effective nuclear charge, and the energy of the metal d orbitals being lowered. So high oxidation states favor lower energy metal d orbitals. All right. What's also favorable is that we have few or no d electrons. And that is because when we have few electrons, then we have little electron repulsion. And electron repulsion tends to increase the energy of orbitals. All right. So now that explains why, for instance, permanganate or dichromate are so intensely colored. They are examples of ligand to metal transfer transitions. So manganese, for instance, is in the oxidation state +7 in the permanganate ion. All right. So we have a very high positive charge at the metal. At the same time, we have no d electrons because manganese 7 is a d0 species. Okay. Same with chromium 6 is also a d0 species with chromium in a very high oxidation number. So similarly, titanium 4 is a d0 species with a titanium also in a high oxidation number. Okay, now what about the ligand properties? So with regards to the ligand, it's of course good when the ligand molecular orbitals have a high energy. Okay, the higher the energy of the ligands, the closer they come to the energy of the metal d orbitals. So that is typically the case when we have pi donor ligands, not pi donor electrons, but pi donor ligands, because we have a lot of electrons available that can be excited in the metal d orbitals, and there's a strong electron repulsion in the orbital, which tends to raise the energy of these orbitals. Okay. Also, negatively charged ligands are favorable for the same reason. We have more electrons, a high negative charge, therefore stronger electron repulsion, which increases the energy of the ligand orbit. So examples for that are, for instance, O2 minus, Cl minus, bromide minus, iodide minus. Okay, so again, that explains why, for instance, manganese permanganate is deeply colored. Not only is the manganese in the oxidation state +7, it has also O2 minus ligands, which are strong pi donors and have a high negative charge. Okay, so here you just see again the permanganate as an example. See that extremely. That's because of the ligand to metal charge transfer. Okay. Now this is also spin allowed and report allowed, which contributes to the intensity of the color. So even at very low concentrations, you can observe the color. Okay, then on the other hand, you can also have the metal to ligand charge transfers. So now these are favored by metal ions that have high energy d orbitals. Okay? So that is favored when the charge at the metal ion is low and when there are many electrons present. So examples for that are, for instance, copper 1 or D10 ions in general. Especially when they have low charge, like copper 1. Okay, so now what are ligand properties? Well, for the ligand, we would like to have pi star orbitals, which are rho-line in energy. And that's the case when the ligand is a good pi acceptor. Then the pi star orbitals have low energy. Okay, so examples are, for instance, 110 phenanthroline, C minus, CO in particular, also thiocyanate is an example. So here's just one example for that, which I already mentioned previously, that this is the bisphenanthroline copper plus, which is dark orange. So here you have copper 1, which is a D10 ion with only a 1 plus charge. And you have these phenanthroline ligands, which are good pi acceptors because of the extended pi system. Okay, so again, these are spin allowed and report allowed, so the intensity of the color is high. All right, then we are at the end of the chapter about electronic spectra. In the next class, we can then start to look at reactivity of coordination compounds and reactions with. All right, then. We can stop the recording at this point.